Okay. The next test that we're going to be looking at to determine if a series converges or diverges is called a direct comparison test. And basically it is when you compare a series to another series that you already know information about. For example, we know that 1 over 2 to the n is a geometric series, and I know in this problem r is 1/2, so I can say this converges. But this looks very similar to this geometric series, but it is not a geometric. So we're not sure exactly what happens to this. 1 over n squared is a p-series, and we can say it converges. But again, we don't know what happens to this one because it looks very similar to a p-series, but because of this extra plus 1, it is not a p-series. This next one, you can use the integral test to determine whether it converges or diverges. And this one looks very similar to it, but it's not exactly the same. So what we're going to be doing is finding a series that looks very similar to a simple one that you know information about to determine whether it converges or diverges. This is the general note card for the direct comparison test, and I will come back and talk about it in a minute, but let's go through some examples first. So I want to figure out whether this series, sigma 1 over 3 plus 2 to the n, converges or diverges. Now when I look at that series, you want to try to identify a series that resembles it very quickly. And I notice it resembles this geometric series 1 over 2 to the n. It just has an extra 3 plus there. So I can say for sure that this is a series that converges because our value is 1/2 and is geometric. Now what we're going to be doing is we're going to compare the two series. So I know for every value of n equals 1, n equals 2, etc., this series is always smaller, or the term that you get from this series is always going to be smaller than this term right here, because when you add a number to the bottom of the fraction, it makes this entire fraction smaller. So for every value of n, this number will always be smaller than this one. So in order to determine whether it converges or diverges, if something converges, then anything smaller than that will also converge. So if you can tell me this is a geometric series that converges, and you can show me that this series is always smaller than this one, then we say by direct comparison test, this converges also. So the first conclusion that's written on this note card, this one right here, basically says that if something converges, then anything smaller than that should also converge if a sub n is always less than b sub n. Okay, so let's try this one. So if I look at this particular series, I notice there's a p-series inside of there. So I'm going to go ahead and compare it to this particular p-series, 1 over square root of n. So this is a p-series that I know diverges. Oops. I want to compare it to this one right here. So we have to figure out what is the inequality. Now here what you're doing is you're just subtracting a number from the bottom. So if you subtract a number from the bottom of the fraction will get smaller, but the entire fraction gets bigger. So I can say for sure that this term will always be bigger than this term. So if this is a p-series that diverges, if something small diverges, then you can also conclude that anything bigger than that will also diverge by dct. And this is the work that you would show. Show me what you're comparing it to, tell me what you know about that series, show me the inequality, and then draw the conclusion about that particular series. Okay, let's do one last example. Let's look at this one. Okay, I see another p-series in this one, so I know that the series that I'm going to compare it to is this. So this is a p-series, and I know that it converges. Okay, next, let's go ahead and compare it to this one. So here I am adding a number to the bottom of the fraction, which makes the bottom bigger, but really the whole fraction gets smaller, so I can conclude that this is always smaller than this one. So if something converges, anything smaller will also converge by DCT. Now this particular problem, instead of doing direct comparison, you could also do the integral test. So it's up to you to decide which test is an easier method for you. So if you choose to do the integral test, you are integrating from 1 to infinity 1 over x squared plus 1 dx. This is going to be your arctangent. Rewrite it with the limit statement. This is really pi halves minus pi fourths. So using the integral test, you can also say it converges. So there are two different ways to do this one particular problem.